Let's now solve a few problems based on the material that was covered in this week. The first problem is to show that if you are given a function which is holomorphic on a simply connected domain and which does not vanish on omega, then there exists a holomorphic branch of the nth root of f. So let me write down the problem for you. The first problem is the following. Let omega be a simply connected domain, simply connected open connected set. Okay, so that's something which I will implicitly assume in this lecture, simply connected domain, and f from omega to c star, let me put c star here, be a function which is holomorphic on omega. So notice that f does not vanish, that's what it means. Then f does not vanish on omega. Then prove that there exists a function, let's call it something h from omega to c such that, c star to be more precise, such that h of z to the power n is equal to f of z. There exists a function holomorphic such that h is holomorphic and this is happening. And h of z to the power n is equal to f of z. Let's give a proof of this. We have seen a part of, in fact most part of this proof already once, but it's good to recall in the setting now because we have seen what is meant by the holomorphic branch of the complex logarithm. So let's just recall what we had done earlier some time back when we proved Cauchy's theorem. The first observation is that since f is non-vanishing, because f takes values in c star, f prime by f is holomorphic on omega. That's the first observation. Now f prime by f being holomorphic on omega and omega being simply connected, then for any closed curve gamma on omega, we have the integral of f prime over f is over gamma is equal to 0. This is by the Cauchy's theorem. Now by the fundamental theorem of calculus, the second fundamental theorem of calculus to be more precise, by the fundamental theorem of calculus, there exists an antiderivative. There exists an antiderivative g of f on omega, g of f prime by f on omega, let me be precise, and our antiderivative can be picked in such a manner that the antiderivative is uniquely defined up to addition by a constant. So let's normalize it, which will be useful for us later. Let z0 in omega and w0 in c star be such that f of z0 is equal to w0. Let's pick our g and g be picked in such a manner that e to the power g of z0 is equal to w0. You can always do this because w0, remember, is a non-constant, non-zero constant, and the exponential is a map from c into c star, and therefore c onto c star, and therefore you can add g by the relevant constant to arrange for this to happen. So once we have this, let's now see what happens to our function g of z. So remember that g of z is the primitive of f prime by f. Now consider the following function exp of g of z by f of z. Let's consider this function and let's look at its derivative. D by dz of this function. Let's look at what happens here. By the quotient rule, we have f prime of z times exp of g of z minus f of z times the derivative of exp of g of z, which is exp of g of z, times g prime of z, which is f prime of z by f of z, whole divided by f of z square. If you notice, f is non-vanishing and therefore all this makes sense, and we are ending up with just 0 here. And being an open connected set, what was the derivative of? The derivative was of exp of g of z by f of z. This is going to be some constant. And what did we arrange for? How did we arrange for g? G was picked in such a manner that at z0, exp of g of z0 by f of z0. If you look at this, this is exactly equal to exp of g of z0 was f of z0, isn't it? The w0, and this is exactly equal to 1. So what we have just arranged for is a function g which satisfies the condition that exp of g of z is equal to f of z. If you notice, we have just mimicked what was done when we wanted to catch hold of a holomorphic branch of the logarithm function. This is logarithm of a function f, but yes, this is worthwhile an exercise to go through once more. And finally, let me just define. Let's define h of z to be equal to exp of g of z by n. Notice that g of z is a holomorphic function on omega, g of z by n is a holomorphic function, x is entire, so x composed with g of z by n is also going to be a holomorphic function on omega. And it's very easy and straightforward to sit down and check that h of z to the power n, this is going to be x of g of z, which is equal to f of z. And that's precisely what we had set out before. The next problem is going to be a simple and nice application of the Schwarz's lemma. Let me state the problem. The problem has something to do with holomorphic self maps of the unit disk. So let f from D to itself be a holomorphic map with two fixed points. Then prove that f is necessarily the identity map. There cannot be two fixed points. That's precisely what is trying to be conveyed here. Let's give a proof of this statement. Let's pick the two fixed points arbitrarily. Let alpha and beta be such that where both are points in D. Let them be 2 points such that f of alpha is equal to alpha and f of beta is equal to beta. Then let's define the following map. Define g of z to be equal to phi minus alpha. Phi minus alpha is just z plus alpha by 1 plus z bar, 1 plus alpha bar z. And notice that this sends 0 to alpha, and when you compose it with f, that sends alpha back to alpha, and then when you compose it with phi alpha, that sends back alpha to 0. So this map phi in particular, g of 0 is equal to 0. Also notice that phi alpha, f and phi minus alpha, all the three are maps which map the unit disk to itself, and therefore g is now a map from the unit disk to itself. We also have g of 0 is equal to 0. We are in the perfect setting for Schwarz's lemma, and to apply that, what we can do is let beta prime be equal to phi alpha of beta, and then let's try to see what is g beta prime. If you look at g beta prime, this is going to be equal to what was g beta prime? What was g? G was basically phi alpha composed with f composed with phi minus alpha of beta prime. Let's just go up and have a look at what that was. Yes, perfect. So this is precisely what it is. And phi minus alpha of beta prime is precisely equal to beta. So this is equal to phi alpha of f of beta, but remember that beta is a fixed point of f, and therefore this is going to be equal to phi alpha of beta, which again by definition here, that's just equal to beta prime. So what we have is that g of beta prime is equal to beta prime. So notice that alpha, okay, did I put distinct here in the problem with 2 distinct? Let me just specify that, and because it's distinct, first thing to note is that beta prime is not equal to 0. Beta prime is some non-zero complex number in the unit disk, and we have noted that g of beta prime is equal to beta prime. In particular, by Schwarz's lemma. What does Schwarz's lemma say? Schwarz's lemma says that mod of f of z is less than or equal to mod z. And if mod f of z is equal to mod z, then that implies that f of z is equal to lambda times. So here it is g of z is equal to lambda times z, where absolute value of lambda is equal to 1. But we also know that g of beta prime is equal to beta prime, right? So that means that lambda times beta prime, this is because g of beta prime is exactly equal to beta prime. We have lambda beta prime is equal to beta prime, which tells us that lambda is equal to 1. It's precisely equal to 1. And hence, this tells us that g of z is equal to the identity. But what was g? G was very special. We had defined g in this manner, right? Let's go back, define our g. Phi alpha composed with f composed with phi minus alpha of z. This is equal to z. Because phi alpha is and phi minus alpha both are automorphisms of the unit disk, this tells us that f is equal to phi minus alpha composed with phi alpha of z. And hence, phi minus alpha and phi alpha are just inverses to each other, and hence we get to conclude that f is the identity. And that's precisely what we had set out to prove. Based on the ideas that we used to prove this particular problem, let's now try to give a generalization of the Schwarz's lemma. The name of this theorem is called Schwarz-Pick theorem. Even though I'm just doing it as an exercise, it's quite an important exercise that you should keep in mind. It's a theorem which is very powerful. We will not go into the ramifications of the impact of this theorem in this course. However, let's certainly prove it. So to do that, before I state the problem for you, for z and w in the unit disk, z not equal to w, define rho of z comma w to be equal to z minus w by 1 minus w bar times z, the absolute value of this. Okay, and let's now, so this is some kind of a pseudo distance, let's not bother about that. The problem is the following for you. Let's take the unit disk and a holomorphic self map of the unit disk. Let f from D to itself be a holomorphic map. Then rho of f of z, f of w, this is going to be less than or equal to rho of z comma w for all z and w in the unit disk. Furthermore, the absolute value of f prime of z by 1 minus absolute value of f of z the whole square. This is less than or equal to 1 by 1 minus mod z square, again for all z in the unit disk. Let me just note that this is what is called as the Schwarz-Pick theorem, which you will certainly see later when you do some hyperbolic geometry and define the hyperbolic distance. Let's not again discuss more about those things, rather let's give a proof of this. As I had noted earlier, this statement is going to follow from ideas which we developed in the previous problem. And to do that, what we will implement that, let's follow the same technique. So for W in the unit disk, let G of Z be defined to be equal to, so phi of minus W. This is the automorphism of the unit disk, which is going to map 0 to W, minus W to 0 to be precise, and that's going to map 0 to W. And if you take this point, the image of this point under f, that's going to be f of W, and if you now compose it with p f W, this is a function which is going to be a holomorphic map of the unit disk to itself, and further G of 0 is equal to 0. Notice that G from D to D is holomorphic and G of 0 is equal to 0 by Schwarz's lemma. What do we have by Schwarz's lemma? By Schwarz, we have G of Z, absolute value of G of Z. This is less than or equal to absolute value of Z for all Z in unit disk. So in particular, so I should have maybe used zeros, or maybe we should change this notation to some zeta, because I'm now going to use Z and W's as fixed above. So for Z and W, I didn't fix, but we were trying to prove this for every Z comma W, right? So this is what we were trying to prove, and for that we start off with some Z and W. Of course, now I hope the confusion has been resolved. Now Z has not yet featured into the story. So G of zeta is going to have absolute value less than or equal to zeta, absolute value of zeta for all zeta in D. Let's now pick Z prime to be equal to phi W of Z, and let's look at what happens in the equation that we have just defined at Z prime. So star is going to give us, by star we have the absolute value of G of Z prime. This is less than or equal to absolute value of Z prime. Notice that for Z in D, phi W of Z is also going to be in D, so Z prime in particular is going to be in D, and this is satisfied by our function G. But what does that mean? What is G of Z prime? G of Z prime, that's going to be equal to, let's write down what G was. G, recall, was phi f W composed with f composed with p minus W of Z prime. But what is Z prime? I recall that Z prime is phi W of Z. So this is going to be phi W of Z, which is going to be equal to phi f W of f of Z. And that's going to be equal to f of Z minus f of W by 1 minus f of W bar times f of Z. Therefore, absolute value of G of Z prime, this is equal to the absolute value of f of Z minus f of W by 1 minus f bar W times f of Z, which in particular is equal to rho of f of Z f of W. That's good, because we have realized the left hand side as the left hand side in this inequality. And what's going to be absolute value of z prime? Absolute value of z prime is just absolute value of phi w of z. What is that? That's precisely how our z prime is being defined. The manipulations were perfect in the sense that the right hand side is going to end up with absolute value of z minus w by 1 minus w bar times z, and that's precisely equal to rho of z comma w. So what we have is the inequality rho of f of z f of w is less than or equal to rho of z comma w. So the moment we have a holomorphic self map of f of the unit disk, it satisfies this inequality with respect to rho. So it's a good exercise to sit down and conclude that if f is an automorphism of D, then this above inequality is an equality. Then the above inequality is an equality. The Schwarz theorem will be complete if I prove this part as well. In order to do that, we have to show that f prime of z, absolute value of f prime of z by 1 minus the absolute value of f of z the whole square is less than or equal to 1 by 1 minus mod z square. Let's prove that. So what did we just establish? We just established that for all z comma w, we have z comma w in the unit disk, we have the absolute value of f of z minus f of w by 1 minus f of w bar times f of z. This is less than or equal to 1 by, less than or equal to absolute value of z minus w by 1 minus w bar times z. This absolute value. Now, if we take z not equal to w, and for z not equal to w, let's see what happens. We divide the entire equation by 1 by absolute value of z minus w, and we have f of z minus f of w by z minus w times the absolute value of 1 by 1 minus f of w bar times f of z, which is less than or equal to 1 by 1 minus w bar z. Now, if you take the limit as w goes to z in the unit disk where w is not equal to z, because f is a holomorphic function, let me just write that part down. By taking limit as w goes to z, we have absolute value of f prime of z times 1 by 1 minus absolute value of f of z the whole square. The whole absolute value can be now taken off because f is a map from the unit disk to itself. So absolute value of f of z square is less than 1, and 1 minus absolute value of f of z square is a positive number. So the absolute value here can be removed, it's not needed. Similarly, when you take the limit in the right hand side, this is going to be 1 minus mod z square, and again I can remove the absolute value because this is the positive number, the positive quantity. And this is precisely what we were trying to prove. And with this, we have completed the proof of the Schwarz theorem. Let me conclude this problem session by characterizing all those holomorphic maps from omega to the complex plane which preserves the unit circle. Let me state the problem. In fact, I'll be a little more specific. Let f be an entire function such that absolute value of f of z is equal to 1 for all non-constant. Let me just put in that extra condition. Let f be a non-constant entire function such that absolute value of f of z is equal to 1 for all mod z equal to 1. So unit circle is preserved by the function f. Then describe f. So I am leaving it vague. We will see that we can give a very concrete description of this particular function. So the only information that we are given about this function, so I should point out that it's enough for f to be holomorphic in a neighborhood of the closed unit disk for this particular conclusion to be drawn by us. Whatever we conclude about f will be true even in that case. Let me give a proof of rather I will call it a solution because we don't know what to prove here yet. Let's see what happens when we explore what happens to this function f. The first observation is that by the maximum modulus principle, what do we have? We have absolute value of f of z. This is going to be less than or equal to 1 for all z in the unit disk, because on the boundary of the unit disk, so the compact set K being equal to d bar, we apply the maximum modulus principle and we will be able to conclude this. So f is now going to be a map from D to D. That's precisely what we just concluded. And my first claim is that such an f should necessarily have a 0 in the unit disk. So let me write the claim down for you. F has at least 1 0 in D. So let's see what happens if that's not the case. Suppose f doesn't have a 0 in D. If f does not have a 0 in D, then 1 by f is holomorphic on the unit disk, and furthermore 1 by f extends continuously up to D bar and continuous on D bar. Because f is continuous on D bar and does not vanish on D bar, 1 by f also is going to be continuous. And by one of the variants of the maximum modulus principle which we stated, 1 by f of z, because it's equal to 1 on mod z is equal to 1, we have by one of the variants of the maximum modulus principle which we described in this week, we have 1 by absolute value of f of z is going to be less than or equal to 1 on the unit disk. But that's precisely going to manifest as demanding that absolute value of f of z is greater than or equal to 1 on D. But we already have by the maximum modulus principle that the absolute value of f of z is going to be less than or equal to 1. And in conjunction with f of z absolute value greater than or equal to 1, which we just concluded, we have absolute value of f of z is equal to 1 on the unit disk. But is that possible? That's not possible, because if f is a non-constant holomorphic map, it's an open mapping and f of D is going to be an open map. And by open mapping theorem, f is forced to be constant, because if f were not constant, then f of D has to be an open set and it cannot be contained in the unit circle. So by open mapping theorem, f is constant, which is a contradiction to the very assumption that we started off with a non-constant holomorphic mapping. Let me just go up and check for you that we started off with a non-constant holomorphic mapping. So what have we ended up with? We have shown that this has to be true. This has to be true. We have established the claim. Now my next claim is that one cannot have infinitely many zeros in the unit disk. So the next claim is going to be the following. F has finitely many zeros in D. That's quite a straightforward observation, because we started off with an entire function, and if it has infinitely many zeros in D, in particular it will have infinitely many zeros in D bar, and D bar being compact, this will have a limit point, and by the identity theorem f is forced to be the identically zero function, which is a constant, which is again a contradiction. So let me write that down. If f has infinitely many zeros in D, in particular in D bar, then the zeros of f has a limit point by compactness of D bar. By compactness of D bar, we will be able to get hold of a limit point, and this would imply that f is identically equal to 0, a contradiction to the fact that f is non-constant. The identity theorem, this is what by identity theorem tells us that the zeros of a holomorphic function cannot have a limit point unless f is identically equal to 0. And therefore, we have our claim f has only finitely many zeros. So let's list these zeros out. So let alpha 1, alpha n be zeros of f. Now let's consider the function which we have considered most in this particular week. Let's consider the automorphism of unit disk which maps alpha I to 0. But before that, let alpha 1, alpha 2 up to alpha n be zeros of order d1 to dn. This means that f of z is going to be equal to z minus alpha j to the power dj times a function g subscript j, where gj of alpha j is not equal to 0. Okay. So we in fact have a gj which does not vanish. So in particular, what can we say? Then we can say that f of z is equal to z minus alpha 1 up to z minus alpha n times d1 to up to dn times g of z, where g is a function defined on the unit disk which does not vanish. Alright, so let's now consider the following function. Consider phi alpha j of z. Phi alpha j of z is having a 0 at the point alpha j, but being an automorphism, you can sit down and check that phi alpha j prime at the point alpha j is not 0. It cannot be 0. The function phi alpha prime is not going to vanish in the unit disk, and therefore alpha j is going to be a 0 of multiplicity 1, and therefore if you consider phi of alpha j to the power dj, so let's come to that in a minute, this is going to be equal to z minus alpha j times psi j of z, where psi j does not vanish on the unit disk. Remember that psi j of z, if psi j vanishes in the unit disk, then phi alpha j also vanishes at that particular point. However, for z not equal to alpha j, phi alpha j of z is not equal to 0, and therefore psi j of z is not equal to 0. And at the point z equal to alpha j, we have just noted that it's a simple 0, and therefore psi j is not going to vanish. Now if you consider phi alpha j of z to the power dj, this is going to be equal to z minus alpha j to the power dj times psi j of z to the power dj. Now let's define a new function. Define g of z to be equal to, we started off with our function f of z which has zeros at z1 alpha 1 alpha 2 up to alpha n, each of which has order d1 d2 up to dn. Now if you look at the function g of z by phi alpha j of z to the power dj multiplied all the way with phi alpha, so this is phi alpha 1 d1 all the way up to phi alpha n of z to the power tn. If you consider this function, the first observation would be that absolute value, okay, g of z is a meromorphic function. G has singularities. Let's not assume any of the things about the singularities yet. G has isolated singularities at alpha 1 all the way up to alpha n. So let's focus on alpha 1. The argument at all other places is going to be similar. If you focus at alpha 1, f of z is going to be equal to z minus alpha 1 to the power d1 times some f1 of z, where f1 of alpha 1 doesn't vanish. And if you focus on phi alpha 1 of, so phi alpha 1 we will write later, but phi alpha 2 of z all the way up to phi alpha n of z to the power dn. So let me put all that. Phi alpha 2 of z does not vanish at alpha 1. Alpha 1, alpha 2, alpha n are distinct roots. So phi alpha 2 of z is not going to vanish at alpha 1. So this is going to be a function which is holomorphic in a neighborhood of alpha 1 and which does not vanish, and therefore 1 by whatever is in the bracket is going to be a holomorphic function. And what do we know about phi alpha 1 of z? That's going to be equal to z minus alpha 1 to the power d1 times, what did we call it, some psi j of z to the power d1, which does not vanish at alpha 1. So you should now sit down and check. So let me just give it as an exercise for you. I have done all the hard work for you now. Just check that. Oh, this is not g, by the way. This is after the division. This is going to be g, right? Right. So this is our g. I divided it here. So let me call it g and not create confusion. So the exercise is to show that g has a removable singularity at alpha 1. In fact, exercise is to show that g has a removable singularity at alpha j for 1 less than or equal to j less than or equal to n. So each of these alpha j's, this is going to be a removable singularity. Now let's again check what is g of z for z in mod z equal to 1. What is this going to be? This is going to be equal to the absolute value of f of z by absolute value of phi alpha j of z to the power d1 all the way up to phi alpha, in fact 1 to the power d1 to phi alpha n of z to the power dn. Each of these numbers are going to be equal to 1, and hence this is going to be equal to 1. We have already checked that phi alpha j's are going to preserve the unit circle. So this is going to be equal to 1, and by a very similar argument, if g does not have a 0 in the unit disk, then g is going to be a constant. But notice what we have done here. So again, next exercise for you. G does not vanish in the unit disk, and by the maximum modulus principal argument above, let me just write it as by a similar argument as above, we have the absolute value of g of z is a constant function. and we also know that absolute value of g of z is equal to 1, and therefore the constant has to be a point on the unit circle. So this means that g of z is equal to some lambda where absolute value of lambda is equal to 1. Therefore, what do we know? We know that what is g, i.e. f of z is equal to lambda times phi alpha 1 of z to the power d1 all the way up to phi alpha n of z to the power dn. So this is precisely the description of a function. So let me just recall for you what we were trying to do. We were trying to describe the function f, which is a non-constant entire function which preserves the unit circle. This is what is very classically known as the finite Blaschke products. Let me not go into more technicalities there. Let me stop here.